Okay, welcome class to Physics 390 Class 7. This class will be on the TISC potential wells and scattering. And we'll be looking at potential wells which can have bound states, which are restricted to the well, and also scattering states, states which come in, interact with the well, and then go off in the other direction. So this covers chapters 2.5 to 2.6 of our textbook. So let's get started. So we'll start off by defining bound states and scattering states. And then we'll look at the first of our two well functions called the delta function well. So as I just suggested, bound states are restricted to a finite range of positions. Okay, so an example of this that we've looked at is the infinite square well, where the states are confined to the region between 0 and A, that is the region where the well is. They can't go outside that, so they're bound states. Scattering states, on the other hand, range over all space. So for example, the free particle stationary states, the complex exponentials e to the I kx, those range over all space. So those are called scattering states. And in quantum mechanics, the conditions for bound states and scattering states are as follows. If your energy is less than the potential at as you go to minus infinity, and also less than the potential as you go to plus infinity, then the energy is bound by those high potentials at plus and minus infinity. And so you have a bound state. And you can see that here. So this is the, as we go to minus infinity, this potential increases. As we go to plus infinity, this potential increases. And the energy here is less than that potential as it goes off, as x goes to minus infinity and x goes to plus infinity. So we'll have a bound state of this potential here. Just incidentally, these are the, if this was a classical system, the energy would be restricted to between these classical turning points. For quantum systems, there's a possibility of the wave function actually being outside of the classically allowed region. Anyway, that's sort of a bit of a digression, but still an interesting little tidbit. So what about scattering states? For scattering states, we need to have the energy greater than the potential as x goes to minus infinity, or greater than the potential as x goes to plus infinity. So that would be a scattering state. So this this state here, where the energy is greater than what the potential goes to as x goes to minus infinity, and greater than what the potential goes to as x goes to plus infinity, that is a scattering state. And even if this this potential on to the right went above E, it would still be greater than the potential at as x goes to minus infinity. So it would still count as a scattering state. In that case, the particle would basically come in and bounce off of the potential and come in from the left and bounce off and go back to the left. Okay, so so let's look at these bound states and scattering states. As we said, the infinite square well has only bound states. The free particle has only scattering states. A nice first model potential, which has both bound and scattering states, is built from something called the Dirac delta function. The Dirac delta function is a very sharp spike at the origin or at a particular x value. So it's written with a delta, a lowercase delta, which is why it's called the Dirac delta function. And it's defined to be 0 if x is not 0 and to be infinite if x is equal to 0. Okay, so it's since it's discontinuous, it's not technically a function. It's called a generalized function, but it can be made mathematically rigorous with the right function and limits. But another property it has is that if you take the area under the delta function curve, so for the integral from minus infinity of the delta function dx, you get 1. So it has unit area. So it's very, very high, a sharp spike. It's very, very high, but very, very thin. And in the limit, it's such that that area, it gets very high and very thin in such a way that the area goes to 1. Okay, so it has an interesting property. So if we look at a delta function that instead of being centered at at the origin at where x equals 0, where x minus a equals 0, or at another way of putting that is x equal a, then if we multiply by a function f of x, this will be 0 except at x equal a. So if x is not equal to a, this will be 0. So we can replace f of x by f of a, since that's the only f of x which is non-zero. So we just get is equal to f of a delta of x minus a. Okay, and that property gives rise to the sort of the characteristic, along with the area being 1, the characteristic property of the delta function, which is that if you integrate from minus infinity to infinity, a function times the delta function at x equal a, that's going to pick out the value of the function at f equals a. And we can see that because if we use this property here, this just becomes, this f of x times delta of x minus a becomes f of a, but f of a is a constant, so we can pull it out in front. So we have f of a now times just the integral of the delta function, which is 1 by the definition of the delta function. So we just get f of a back. So anytime you integrate over a delta function, it picks out the value of the whatever function is inside at that particular value of where the delta function is centered. Okay, so that's the delta function, kind of a unusual thing, but useful and gives some nice properties, as we'll see. So let's consider the potential v of x is minus alpha delta function of x with alpha positive. So it would look kind of like the delta function, but spiked down instead of spiking up. And the it's multiplied by this factor of minus alpha to give the strength of the potential. So the bigger alpha is, the stronger the delta function would be. Okay, so let's look at this and analyze this and see if we can make some sense of why the delta function has bound states and scattering states and what they might look like. Okay, so bound states for the delta function well, the delta function again is minus alpha times the delta function at the origin. Here's the TISE for the where we've plugged in for v of x, the minus alpha delta x. Okay, so this is the equation we're trying to solve. So if we're looking at bound states, we want E to be less than 0 because the potential at infinity is, or the potential at minus infinity and plus infinity for the delta function is 0. So to have a bound state, we need to have an energy less than 0. So it's less than the potential at x as x goes to minus infinity and infinity. So for x negative, we have, let's see, we can write this for x negative, this delta function disappears, okay? Delta function disappears because it's only at x equals 0 that the delta function has a particular, any non-zero value. So we can write this multiply through by minus 2m e over h bar squared, and we get this equation here. Second derivative of psi with respect to x squared is minus 2m e over h bar squared psi. Now, remember, e is negative here. So this whole quantity minus 2m e over h bar squared is a positive number. So we're going to write that as kappa squared. So to emphasize that it's a positive number, and also to get a nice solution to this equation. So this becomes kappa squared psi, where kappa is the square root of this whole thing here, which would be the square root of minus 2me over h bar. And remember, again, energy is less than 0, so minus 2me is positive. So this positive square root is a real number, not an imaginary number. Okay, so what solutions do we get here? Well, we get actually two solutions. We get a solution e to the kappa x and a solution e to the minus kappa x if you solve this equation here. But the e to the minus kappa x, as x goes to minus infinity, since we're looking at x less than 0, will blow up, because e to the minus kappa x, as x is negative and getting very, very negative, will get very, very large. So that's not normalizable. So what we want is e to the kappa x, because when x goes to negative infinity, this e to the kappa x will decrease to 0, and the function will be normalizable. So that's the solution we're looking for. So if we go through a similar argument for, again, a bound state e less than 0, but x greater than 0, okay? So we get the same equation here, the same kappa, everything's the same. But now we want the solution with e to the minus kappa x, because if x is going to positive infinity, we want minus kappa x, because e to the minus kappa times a positive number will be, a large positive number will be very small. So the solution will go to 0 as x goes to infinity. So these are our two allowable solutions. And this is kind of what they look like. For positive x, it's e to the minus kappa x. It has some amplitude, which we'll calculate in a minute, but it goes down as e to the minus kappa x. So it's this decreasing exponential. And it's for x negative, it has a similar behavior, because this is e to the kappa x for x negative is going to follow this curve here. So it looks like kind of a cusp type potential. So how do we make further progress? We have these two solutions, but we have several unknowns, B and F, and the energy E of our bound state. So what we can do is impose continuity of the wave function at x equals 0. Okay, so there must be some well-defined probability density at x equals 0. So the wave function should have the same value for the solution from the left as it does from the solution from the right. So if we plug in x equals 0 here, we get 1 and 1. So we get just psi 0 is equal to b, psi 0 is equal to f, but those should be equal. So f is equal to b. So they're actually both, so we can just replace this by b. So we get, our solution is b e to the kappa x for x negative, and b e to the minus kappa x for x positive. Okay, now some interesting things happen. Normally, the derivative of the wave function is also continuous. But we can see here that that's not the case, because when we come in from the left, the derivative is positive. when we come in from when we go out from 0 to the right, the derivative is negative. So there's a cusp or a kink in this function right at this point. And that's caused by the delta function. And we'll see how that works in a second. So if we take the derivative of these functions for x, so this is actually x less than 0 here on the lower one, we get, we pull down a kappa. So we get beta kappa e to the plus kappa x. On the other hand, if we take the derivative of for x greater than 0, we get minus beta kappa e to the minus kappa x, which is this top here. So if we look at it as we approach 0 from the x positive, we get the derivative would be plugging in, this will get closer and closer to 0. So e to the 0 will get, e to the x will get closer and closer to 1. So as we get closer and closer to 0 from the positive side, we get minus beta kappa. On the other hand, here we can see that as we get closer and closer to 0 from the negative side, this will go to e to the plus kappa x will go to 1, and we'll get plus beta kappa. So we can see the discontinuity here. It goes from a positive derivative with magnitude b kappa, and to a negative derivative with magnitude, or not magnitude, but negative derivative with value minus b kappa. So there's this discontinuity here. Okay, so the discontinuity in the derivative, which we see here in the picture and in these values, can be related to the strength alpha of the well. Okay, so to do that, we take the time-independent Schrodinger equation up here, and we integrate it from minus epsilon to plus epsilon. So just a small, tiny window around x equals 0. Okay, so we just take this equation here, we integrate it from minus epsilon to plus epsilon, each term. And here we've left v of x instead of putting minus alpha delta x, but that's what this actually is, minus delta alpha x here. It's going to become that in a second. So looking at these terms as if we take the limit as this little window gets small in size, the integral of the wave function is just going to go to 0 because it's finite. The wave function is finite, and as the window size shrinks, this will go to 0. On the other hand, the first term here is going to limit to, as no matter how small we make epsilon, the integral of the second derivative is the first derivative. So it's going to be the first derivative evaluated at a positive epsilon, like right here, minus the first derivative evaluated at a negative epsilon. And even in the limit, as epsilon goes to 0, because epsilon never gets to 0, that is going to have a finite value because of this kink here. Okay, so we call that the change in the derivative is this limit of the difference between the derivative between the two sides. Okay, so let's see. So we take that, move this. This is, as we argued, this right side here is 0. So we move this term here over to the right side, multiplied by 2m over h bar squared, and we get the change in the derivative is equal to 2m over h bar squared times the integral from minus epsilon to plus epsilon of v of x psi of x. And that's what we have here. But remember, v of x is minus alpha delta of x. So if we plug in minus alpha delta of x here, that is going to, that integral is going to pick out the value of psi at x equals 0, because we're going to be integrating delta of x over a range which contains x equals 0. So it picks out psi of 0. So this just becomes the change in the derivative from one side to the other is minus, because of the minus sign in the potential, 2m over h bar squared times the alpha from the potential, and then excuse me, the delta function picks out the phi of 0 here. Okay, so this is the discontinuity in the derivative related to the strength of the potential alpha, the strength of the delta function well. Okay, so we have, now we know that we know psi, we have the form for psi. So if we put in psi 0, we get psi 0 is equal to b. Okay, so we have psi 0 equal b. So we can write this, let's see. So the change in the derivative as we go from one side to the other would be minus b kappa, which is on the positive side, minus the value on the negative side, which would be minus b kappa again. So minus 2b kappa is the directly evaluated change in the derivative. But that's supposed to be equal to minus 2m alpha over h bar squared psi of 0, where psi of 0 is b. So that's minus 2m alpha b over h bar squared. Okay, so crossing out the minus 2b, we get kappa is equal to m alpha over h bar squared. Okay, so great. So we've done a lot of work with this derivative and this kink. So what does that tell us? How is that getting us closer to the bound state? Well, kappa, remember, is related to the energy. So we can find the energy now because we found kappa in terms of our mass, a constant h bar, and the strength of our potential. So this gives the energy for the single bound state. The delta function well has a single bound state, just one, which would be solving for this. Let's see, squaring both sides, we'd have h bar squared kappa squared is equal to minus 2m e. So divide by minus 2m and we get minus h bar squared kappa squared over 2m, which can be rewritten using this kappa here as minus m alpha squared over 2h bar squared. So that's just another way to write this. If we put in this kappa squared and simplify, we get this value here. And notice this is negative, and we want that because it's a bound state. So this is negative. So that's our single bound state. And then we can normalize. We have the wave function. We know kappa. So we can integrate this from minus infinity to infinity and find the value of b that makes the normalization give 1. And that turns out to be square root of kappa, which is the square root of m alpha over h bar. Okay. And that gives us our bound state, because now we know b, the normalization constant, and we know kappa. So it would be equal to our bound state is pictured again here, but now we see the magnitude of it is square root of kappa. That's the normalization constant. And which is equal to square root of m alpha over h bar, this out in front, minus kappa times x. So this would be kappa, which is m alpha over h bar squared, m alpha over h bar squared times x. And this is written in a form that with the absolute value of x that combines the expressions for positive and negative x in one nice expression. Okay. So so we found there's one bound state. Its energy is, the deeper the well and the more massive the particle, the more bound it is, because this is m alpha squared. So the energy would get more and more negative as the well gets stronger. And the wave function, the bound state wave function has this kind of cusp shape. which is given here. Okay, so that's an example of finding the bound state for the delta function well. Okay, but what if the energy is not less than zero? What if the energy is greater than zero? In that case, like we said at the beginning, we get scattering states because for the delta function well, as x goes to minus infinity and positive infinity, the potential goes to zero. So if the energy is greater than zero, we have our energy greater than the potential and we get scattering states. So we start off with the same equation. We're going to analyze the scattering that goes on. So we start off with the same equation, the Schrodinger equation, time-independent Schrodinger equation, where here's v of x, which is the delta function. And we start out very similarly to the bound state, except now we have e greater than zero and x less than zero. So v of x is equal to zero. So this drops out. We get the second derivative of psi is minus 2me over h bar squared psi, which we call minus k squared psi, because here e is positive. So this whole term here is negative. So we have to write it as minus k squared. And since e is positive, k, in order to be real, we have to take the square root of 2me as opposed to kappa, where we took the square root of minus 2me over h bar. So notice this is the same expression as for the same differential equation and the same k as for the infinite square well, because we have v equals 0 and positive energy. So it's the same setup. So that gives we're going to write those as the solution in terms of complex exponentials. So it'd be a e to the I kx plus b e to the minus I kx. Okay, so a similar argument for, again, energy greater than 0 for the scattering state, and x greater than 0 gives a solution, another solution with different coefficients, possibly f and g. Okay, so let's start. So these are our two solutions. Now we have to try to narrow things down and start solving things. So the continuity of the wave function at x equals 0 says that if we plug in x equals 0 in all of these places and set these wave functions for x negative and x positive equal to each other, we should get an identity. So with x equals 0, all these exponentials go to 1, and we get a plus b is equal to f plus g. Okay. Now we can go through, there's going to be a discontinuity in the derivative at x equals 0. Okay. For the same reason as we had it before, if we, for the bound state, if we integrate this Schrodinger equation over the a small interval, it's going to show us that there's a change in the derivative that occurs. And the discontinuity in the derivative is analyzing it is a little bit involved. It's algebra, but there's a lot of algebra. So I'm just going to refer you to the textbook on that. But we get this condition here, which is ik, where k is this constant, times f minus g minus a plus b is equal to minus 2m alpha over h bar squared a plus b. Okay, so this will, for this video, we'll take this as a given, but you can see the textbook if you're interested in how this is derived. Okay, so how do we solve this? Wow, lots of unknowns, right? We have a, b, f, g, and then we're looking for e. So we have really 4 or maybe even 5 unknowns. So let's physically interpret what's going on with this scattering. And to give you a hint, we're going to wind up taking g equals 0, and I'll tell you why in a second. So we're going to interpret the solution to for x less than 0 with a e to the I kx as an incident wave moving to the right, because it's at negative x and it has a positive k, and k is related to the momentum, so it has a positive velocity. So it's flowing to the right, and it's at negative x. So it's we're going to interpret it as an incident wave moving to the right. As you can see in this diagram here, here's the delta function, and this a e to the I kx, we're thinking of that as a particle flowing in from the right, from the left, toward the delta function. The b e to the minus kx, on the other hand, it's on the left side because it's for x less than 0, part of that solution, but it has a minus k, so it has a negative momentum. So we're going to think of that as the reflected wave moving to the left. It's going to come in, and some of the wave will bounce off and come back as the reflected wave. And then f, which is part of the solution for x greater than 0, we can think of as a transmitted wave moving to the right. Okay. And the way we've set it up, we have a incident particle from the left, and we really just we're only representing one particle with our wave function. So it has to be incident from either the left or the right. It is possible to analyze the whole thing with an incident from the right, but we're choosing an incident from the left. So that means this g e to the minus I kx on the right side, which would be an incident particle from the right, is 0. So g is equal to 0. So that's why g is 0, because there's only an incident particle from the left, not from the right, by the way we're choosing to analyze the system. Okay, so now we have an interpretation of what these different terms are: incident, reflected, and transmitted. Okay, so we can now we can solve these equations. Now that g is equal to 0, we have 4 unknowns. So we can solve for b and f in terms of a and k. So so b turns out to be this expression here, I beta over 1 minus I beta a, where beta is this combination here, m alpha over h bar squared k. And f, the transmitted part, is 1 over 1 minus I beta times a. Okay, so what does that get us? Well, we're getting to something that we can physically interpret and make some physical sense of. So we talk about since the probability is proportional to psi squared, the reflection coefficient will be proportional to b squared, since b is the coefficient of the wave function, over a squared, since a is the incident wave and b is the reflected wave. So b squared over a squared, or the b modulus squared over a modulus squared, is going to give us our reflection coefficient. That is the probability that a given particle will come back and be reflected from the potential. Okay, so if you work that out, divide by a, square it, or take the modulus squared, you get beta squared over 1 plus beta squared. Similarly, we can look at the transmission coefficient, which is f, our transmitted wave, f squared over a squared. That's the probability of being transmitted over the probability of being over the incident probability. And that, if you take the f over a, is 1 over 1 minus I beta. If you take that modulus squared, you get 1 over 1 plus beta squared. And notice if you add r and t together, you get beta squared plus 1 over 1 plus beta squared is 1, which makes sense because the incident particles should either be reflected or transmitted. So the total, the sum of the reflection coefficient and the transmission coefficient should be 1, and it is if you look at it. Okay, so this is in terms of beta, which is in terms of k, and which is in terms of E. So just to get a little bit of insight into how the reflection and the transmission depend on the energy, we can rewrite these two if we substitute in beta and then substitute in K and simplify. We get the reflection coefficient is this right here, and the transmission coefficient is this right here. So let's look at what happens if we increase the energy. If we increase the energy, this second term will get greater. So 1 over it will get smaller. So our reflection coefficient should decrease as the energy increases, which makes sense. So more energy, less reflection, and more transmission, because we're putting in a particle with more and more energy, so it's higher and higher. So it's gonna see this delta function less and less, and it will be deflect. The chance that it gets reflected by that delta function is less and less. Okay, so all right, so the scattering states then we think of as these complex exponentials, the incident wave, the reflected wave, and the transmitted wave. And then we can work out the reflection coefficient and the transmission coefficient, and they depend on energy in the way that we would expect. That energy is, as energy goes up, it's more likely to be transmitted than reflected. But you might say, wait a second, we're looking at kind of a dynamical process here, right? We're saying a particle is coming in from the left and it represents a real particle. But these states, as we know from the free particle analysis of the free particle, these are non-normalizable states, right? If we integrate this over even the negative infinity to 0, it's not normalizable. It integrates to infinity. So that's technically true. And it's a little bit of a subtle issue, but you can reanalyze the whole thing in terms of wave packets. As we talked about before, the wave packets are localized particles. So we think of a localized particle coming in, interacting with the delta function here, and some of it coming back, being reflected, and some of it being transmitted. The analysis is quite messy. Often we need computational help with computers, but we can prove that it gives very similar results to this analysis here in terms of the reflection and the transmission coefficient. So even though we've kind of pulled a fast one in that we're saying that a particle is being represented by a non-normalizable state, we get answers which match up what we get if we use a more technically accurate wave packet representation. So that's just to satisfy in case that happened to be on your mind. All right, so so we have bound states, one bound state for the delta function well, and then for energies positive, we have some chance of reflection and some transmission. Let's look at one more potential, and that is the finite square well. Okay, so this is our second example of a potential that can have bound and scattering states. So we can contrast it to the infinite or infinite square well, which we know only has bound states. So this is a potential which has minus V naught between x equal minus a and a. That's just the way it's usually set up to make it symmetrical. And it's 0 for less than negative a and greater than a. Okay, so you can see how it's kind of like the infinite square well. It's just finite depth, so it's called finite square well. Okay, so we're going to go through this one a little bit faster, just looking at the main results of the bound states and the scattering states. So I'm going to refer you to the textbook for full details of all the analysis. So I'm just going to hit the highlights of what are the main takeaways of this these features. Okay, So for x less than negative a, similar to the delta function, we get the solution we want is psi is equal to b e to the kappa x, where kappa is square root of minus 2me over h bar. We're looking at bound states. So again, minus 2me is positive. So that's the same setup as for the delta function for the bound state. For between x equal minus a and a, we find if we analyze it, okay, if we analyze the Schrodinger equation, and again, I refer you to the textbook for the full details. Psi is c, some coefficient c, sine of Lx plus d cosine of Lx, where L is square root of 2m e plus v naught over h bar. Okay. So it's just like the square well, the infinite square well, it's sinusoidal functions inside the well. Okay. But we've got the depth of the well involved in the coefficient, which makes sense. And then for x greater than a, we find the same thing as for the delta function well. We get psi is equal to f e to the minus kappa x, where kappa again is the same thing as before. And we take e to the minus kappa x because we want it to be normalizable. So as x goes to positive infinity, we want this to go to 0. So the whole thing is normalizable. Okay. So I'm going to jump over a lot of steps in the book. I can refer you to the textbook for full details. We impose continuity of the wave function, and in this case, since there's no delta function, there's no spike, there should be continuity of both psi and d psi dx at x equal minus a and x equal plus a. And if we impose that, we can get relationships between b, c, d, and f and solve this system. And we come up with this relationship here, which is kappa is equal to L tangent of L times A. Okay, that's after doing a lot of working with boundary conditions and simplifying the wave functions and imposing these continuity conditions. So remember, kappa involves E, L also involves E, and A is the width of, or 2A is the width of the well. So this, this equation, if we solve it, we're solving for E, because kappa involves only E as a variable and L only involves E as an unknown. And A, we presume we know. But this is a difficult equation. It's called a transcendental equation because it has L multiplied by the tangent of L. So there's no way to solve it analytically. So we can solve this numerically by plotting both sides computationally on a computer for the allowed bound state energies E that make this true. Okay, so the finite square well has to be, this condition on the energies has to be solved numerically. Okay, so it's possible to show that as the well gets deeper and deeper, so as V naught gets greater and greater, that we get actually closer and closer to the infinite square well energies relative to the bottom of the well. And that makes sense because as V naught gets really, really deep, this starts to look a lot like the infinite square well. So it's possible to show that the solutions to this as the well gets very deep are given by the infinite square well energies, which we've seen before. Okay, so that's the bound states. The bound states have to be solved numerically. The energies have to be found numerically. The scattering states, again, I'm going to hit the highlights here. For x less than negative a, we are going to take psi of x equal a e to the ikx plus b e to the minus ikx, because we have energy greater than 0. So that's just like a free particle. And again, we're going to interpret a e to the ikx as the incoming particle from the left coming into the to encounter the finite square well potential, and b e to the minus ikx as the reflected wave going to the left that will come back from the potential. So just like we did with the delta function. But now, unlike the delta function, we have a finite width here. So in between, for e greater than 0, we still have the same, we're still above the well depth. So we still have the same equation for L as we had before. Sorry, the same equation for psi in the finite square well as we had before for the bound states. Okay, and then for x greater than a, we're going to just take an outgoing wave, a transmitted wave, f e to the ikx, where k is this constant again. So g equals 0. There's no incoming wave from the right, just like we argued with the delta function before. Okay, so we find by imposing continuity of the wave function at the boundaries, the two boundaries, and also the derivative of the wave function at the two boundaries, these two relationships here. Okay, so b is equal to all this quantity involving L and A and K times F, and F can be related to A. Remember, B is related to the reflection, F is related to the transmission, and A is related to the incident wave. Okay, so these are kind of they're true, but they don't give much insight. So what we're going to look at, we get more insight by solving the second equation for the transmission coefficient, which is f squared, the transmitted wave squared over the incident wave squared. So f squared over a squared. And we get this expression here, which is actually, it's not t, but it's 1 over t, is this 1 plus this thing involving v naught and e times sine squared of this quantity here. Okay, so it's easier just to plot it. Here's the energy E, and here's the transmission coefficient T. So for E very small, or at 0, let's see what happens. We have, let's see, sine squared, if we put E equals 0 here, we still have something inside here. So sine squared won't be 0. So we're dividing by something getting very small, E going to 0. So this will get very large. So this side will be very large, but that means 1 over t is very large, so t would be very small. So for low energies, for barely positive energies, as E approaches 0, there's almost no probability of transmission. It's almost sure to be reflected. And that's what's shown here. And then it rises pretty quickly. And you notice that even for a fairly low energy, there's a transmission probability 1. And then very kind of counterintuitively, as the energy rises, the probability of transmission actually decreases. And then it kind of waves back and forth, going to 1 periodically and then gradually approaching 1 as the energy gets very large. And we can see these, we can understand these peaks or these points where the transmission probability is 1 by the places where sine squared is equal to 0. Because if sine squared is equal to 0, then this whole second term is 0, and we get t to the minus 1 is equal to 1, or t is equal to 1. So where sine squared is equal to 0, we get these particular points, which are called resonances. So we get full transmission at these particular points where the sine squared is equal to 0. Or another way of saying that is that what's inside here must be equal to n pi, where n is equal to 1, 2, 3, 4, and so forth. Okay, so we get some really interesting behavior with the finite square well. We get the bound states, and there can be multiple bound states. You'll get more and more as the depth of the well increases. But at the same time, we get these scattering of particles coming in, and we get these interesting transmissions for intermediate, low and intermediate energies based on this resonance here. We call it a resonance. Okay, so just to sum up super quickly, we've looked at bound states and scattering states. Bound states are where the potential is, the energy is less than the potential as it goes to plus and minus infinity. And scattering states are where the potential is greater than the energy is greater than either the potential at negative infinity or positive infinity. We looked at the Dirac delta function, and we defined the delta function well in terms of it. And we looked and we saw the delta function well had one bound state, and we solved explicitly for that because the delta function has some really nice mathematical properties. And we looked at the scattering for the delta function, and we found the reflection and transmission coefficients and made sense of how it depended on energy. And then lastly, we looked at the finite square well, and we saw the multiple bound states and the transmission resonances that occur. Okay, so some really interesting kind of behavior and interesting mathematics. Hope you've enjoyed it, and thanks for your attention, and I will see you in class.